Hello everyone, thanks for coming. We're going to do a review of our week 10th lecture today. So first, we talk about some applications of determinants. First of all, we can easily write down the inverse of a matrix using determinant. A inverse equals to C transpose divided by the determinant of A, where C is a cofactor matrix. That is to say, Cij is the determinant of the submatrix after deleting row I and column j with sign negative 1 to the power I plus j. Then we can apply the determinant as a cofactor matrix to solve Ax equals to b using the Cramer's rule. The solution, the jth component in the solution xj is determinant of bj divided by the determinant of a, where bj is a with column j replaced by b. So in this way, we can write down x equals to a inverse b, that is C transpose b divided by the determinant of a, and this C transpose b is a vector whose components are xj. The determinant is the volume of a linear transform induced by the matrix A. For a rectangular box, the determinant of A is a product of each length if rows of A are orthogonal. If the rows of A are not orthogonal, since the determinant is invariant under subtracting multiples of other rows, we can show that the determinant of A is still the product of the volume of the geometric object spanned by the rows of A. Finally, we can use the determinant of the leading submatrix AK to determine the pivots in Gaussian elimination. dk equals to determinant of AK divided by the determinant of AK minus 1. In this way, we can decide whether role exchanges are needed when we are performing the Gaussian elimination. Moreover, even without Gaussian elimination, we can determine the pivot variables by using the determinants of the leading submatrices. Then we introduce the eigenvalues and eigenvectors of matrices. So the transition from linear system to eigenvalue problems would help us better understand the role of matrices when we are considering linear transformations. So determinants link solutions to Ax equals to b to Ax equals to lambda x, and eigenvalues are defined for square matrices to help us determine the values of those lambda. So how are eigenvalues useful? For example, for the ODEs, if we assume the solution takes the form e to lambda tx, then we only need to solve x equals to lambda x. So the eigenvectors for this matrix A lie in the Liouville space of A minus lambda I. This is called the characteristic equation. Usually there is no general formula if the degree of this polynomial is greater than 4. However, intuitively, we still have this equation. We can solve it numerically to get a good approximation of the eigenvalues. For each eigenvalue, there is at least one corresponding eigenvector. Any non-zero multiple of an eigenvector is also an eigenvector. The set of all eigenvectors for the same eigenvalue would form the eigenspace. Also, if we get linear combinations of the vectors in the eigenspace, they would also be an eigenvector, and that is called superposition of solutions to the equation. For triangular matrices, the diagonal entries are eigenvalues. Generally speaking, for general matrices, diagonal entries are not eigenvalues. Also, we can use the eigenvalues to determine stability for linear ODEs. Of course, this is a topic for ODE course. Using the eigenvalues and eigenvectors, we can diagonalize a matrix. If an n by n matrix A has n linearly independent eigenvectors, then it can be diagonalized as S inverse AS equals to lambda, where S is the eigenvector matrix and lambda is the eigenvalue matrix. Specifically, eigenvectors corresponding to distinct eigenvalues are automatically linearly independent. However, not all matrices are diagonalizable because for some repeated eigenvalues, there may not be sufficient eigenvectors in that eigenspace. Repeated eigenvalues do not imply singularity. 0 as an eigenvalue implies singularity. However, diagonalizability depends on eigenvectors. If the eigenvectors could form the whole space, the diagonalizing matrix is not unique, and columns can be multiplied by any non-zero scalar. Specifically, if lambda is an eigenvalue, then lambda k is an eigenvalue for ak, and x is also an eigenvector for the power matrix ak. If S diagonalizes A, it also diagonalizes the power matrix AK. Specifically, for adding two general matrices AB, eigenvalues of AB are not generally the product of eigenvalues of A and B. There is only one exception. If A and B share the same eigenvectors matrix S, then the eigenvalues would multiply because the two eigenvalue matrices lambda 1 and lambda 2, they will commute with each other. Specifically, real matrices can have complex eigenvalues and eigenvectors. Thanks for listening.